Our next speaker for today, Patrick Ng from the University of Hong Kong, who will talk about Carathéodory balls and proper holomorphic maps on multiply connected planar domains. Please.
First of all, I would like to thank the organizer for the invitation and also organizing these mini courses and workshop. So the title of my talk is Carathéodory balls and also something related to a proper map on some planar domain. So let me start with recording the definition for the metric. So here is the formula for the metric. So if you take omega to be a planar domain, not equal to the compass plane, and then you take 2 points in this domain omega, and then we define the distance between them in the sense of Carathéodory by using this formula. So here, this is inverse of a hyperbolic tangent of these numbers here. And this number is given by this Supima here. So the notation I'm using is the following. So H omega here would be the set of all holomorphic map from omega into the standard unit disk D here. Okay. And so if you fix a point set lot here, and then we will look at those holomorphic map which send this set lot to 0. And then the other point set, we look at the value of f, and then take the absolute value, and then take the Supima. Okay. So this C omega star is also called Mobius pseudo distance. For most of the time, I'm going to deal with this distance instead of this one. This pseudo distance was introduced by Carathéodory in 1927, long time ago. And it is known that if you have omega, which is biholomorphic to a bounded domain in C, then this pseudo distance becomes a distance. Okay, and in this case, if you look at the topology induced by these two metric, and they actually generate the same Euclidean topology of the domain omega. Okay. Now, however, there's something strange for this metric space actually, and there are actually quite a lot of unknown problem, I think, open problem related to this metric space. And maybe that's the reason this metric is not as useful as Kobayashi metric. Now, so the problem that we are going to consider is related to open ball defined by this C omega. And here is our convention. So this notation means the open ball with center A and radius R with respect to this metric. And then B bar here stand for the closed ball here. Okay. And so it's not difficult to check that because this metric is continuous. Then if you look at this open ball and then you take the closure with respect to the usual topology from the compass plane, then this set is actually a subset of this closed ball. Okay. And so one natural question is whether these two are the same. And the question was asked by Janitsky, Flu, and Wiki. So they asked whether these two sets are the same all the time. And so the question was posed in a paper in 1992. And then it was repeated in the book, Invariant Metric, and both in the first edition and also in the second edition. So at least up to this point is still open. And so this problem actually has something to do with whether the open ball is connected or not. And we will see the relationship between them later on. Okay. So why they asked this question? So because they actually proved the following result. So they proved that they can find a non-planar Riemann surface M, or for each n greater than or equal to 2, they can find a strongly pseudo-convex domain in Cn. Okay. such that the following two conditions are satisfied. First of all, they can find a ball which is disconnected with respect to this Carathéodory metric, and also is relatively compact in M. And then because of the first condition here, they can actually construct a smaller ball so that the closure is a proper subset of the closed ball. So, and therefore, in either this non-planar Riemann surface, so this is dimension 1, or in a high dimensional case, they can construct example. For example, showing that some balls are disconnected. And then a lateral question would be looking at cases when you have planar domain, okay, for n equal to 1. And in this case, if you take omega to be simply connected, then because in this case, the metric is actually the same as the Poincare metric, and therefore all the balls are connected. So this case is known when the domain is a proper subdomain of C. And then the next case would be when omega is doubly connected. Okay, and then it was solved by Schneider in 2 papers with 2 different proofs. And so the conclusion is in this case, all the open ball, they are connected. Okay. So the remaining case would be you look at planar domain with connectivity greater than 2, greater than or equal to 2. Okay. So sorry, greater than 2. So this is actually what I'm going to talk about. So I'm going to look at some planar domain with connectivity G+1 and G is greater than or equal to 2. So at least 3 here. Okay, and then so together with my collaborator, Tang and Chai, so we were able to also establish some example that some open ball for this kind of domain is disconnected and relatively compact. And also the closure of the open ball is a proper subset of the closed ball. Okay, so that's something I want to demonstrate in this talk. Okay, and therefore basically it solved the problem of them. Okay. Now, so our example is a one-dimensional here. Okay. However, we can also make use of this one-dimensional situation to get some new example in high-dimensional cases. Okay. So the idea is the following. So this is the omega I just mentioned, and then we take the Cartesian product with the n-1 copy of the standard unit disk. Okay. And then such a domain can be shown to be bounded pseudo-convex in Cn. Okay, and for this M, we also have these 2 conditions satisfied. Okay, so now finally we can also prove that this domain here is not strongly pseudo-convex, and therefore this is really a new example, different from the one that they have before. So now I'm going to move to the second part of the title of this talk, which is about the proper map on a multi-connected domain. And here is the explanation why this Carathéodory metric has something to do with a proper map. Okay, so let me just restate the definition for the metric, and I'm going to look at this Möbius distance instead of the original distance here. Okay, so again, we need to basically look at this optimization problem. Okay, so so the function we are going to consider would be holomorphic and send z log to 0. Okay, and it's not clear whether the Supima actually can be attained by some function, but then Grundy in the 1940s, he actually proved that so the extremal function for this optimization problem is actually a proper holomorphic map from omega onto D. Okay, and moreover, the important thing is he actually proved that this proper map has to have a degree equal to the connectivity of omega. Okay, so this is the connection between the metric and also proper maps. Okay, so for this reason, we are going to focus on proper maps on multi-connected domain omega onto the unities. Now, so this result is quite old. It's 1940, and I cannot find much follow-up work with this result. And one thing people may try would be try to get a characterization of this kind of proper map with a degree equal to the connectivity of the domain. Okay, and this is exactly what we were trying to do. So we eventually can get an explicit characterization of this kind of proper map on a non-degenerate finitely connected domain omega. Okay, and so this characterization actually also answer one question posed by Schneider in his paper, another paper. Okay, and so the characterization that we get is quite similar to the famous result of FAT2, which characterized the proper holomorphic map from unities to unities. Okay, so we all know that this kind of proper maps, they are just a finite Brodsky product, and this result has been mentioned a few times in different talks. Okay, now one thing I found out to be quite surprising is if you replace a D here by an annulus, okay. Until very recently, I didn't come across any result of this kind. Okay, so about 4 years ago, Wang and Yin, they were doing complex dynamics, and in one of their paper, they need a result which is about proper map from annulus to the unities, and they actually come up with the following characterization. So our notation here is the following. So AR would be the annulus of this form. So the inner circle would be with a radius little r. And then they prove that there exists a proper map, holomorphic proper map from the annulus to this, if and only if the zeros of F satisfy this condition here. Okay, so unlike the finite Brodsky product case, so there's no restriction on the zeros except those zero has to be inside the unities. But here, in order to get a proper map, the zero need to satisfy this equation here. And so this little d here is actually the degree of F restricted to the inner circle. Okay. Now, if this condition satisfied, they can express this F explicitly as this infinite product here, sort of. Okay. So and this factor is similar to this one. Okay. If any one of you know a result of this type before their work, so please let me know after the talk. Okay. Now, in their paper, they actually also look at proper map of G+1 connected domain. Okay, and with non-degenerate boundary component, and we are using the following notation: gamma log up to gamma g to represent the boundary of omegas. And to state their characterization, let U1 up to UG be the harmonic measure with respect to this boundary curve here. And they also attain the following necessary and sufficient condition. Okay, so to have a proper map from omega to D. Okay, so it's actually given by this system of equation here. Okay, so you see this pk, they are zeros of F. Okay, and suppose the degree of this proper map is n, so you have an n zero here. Okay, and if you restrict F on each boundary curve, and you look at the degree, and then the degree will be denoted by Ni. And if you add up all these boundary degree, then it has to be equal to the degree, total degree of F, which is N here. Okay, and you have this system of equations. So actually there are G equations here, and you have N points here. Okay, so now if you go back to the annulus case, okay, so this equation actually can be restated in terms of this condition here. Okay, so actually the equation is actually coming from this harmonic measure condition. Okay, now the question is, so they basically stop here. So, but a natural question is whether one can find some expression for F which satisfy this system of equation on a harmonic measure. So this is the starting point of our investigation. Okay, so now we are going to apply this harmonic measure condition to a particular type of omega, which is called circular domain. Okay, so by circular domain, I mean you take the standard unit disk, and then you take away a number of smaller circle. Okay, that's smaller disk. Okay, so this is one example, and so this kind of domain is actually quite general because according to a result of Kirby, which generalized Riemann mapping theorem, it says that any non-degenerate finally connected domain is bi-holomorphic to this kind of circular domain. Okay, so from now on, we are going to assume those boundary curves are just circles. So gamma log will always be the unit circle, and then gamma I will be those inner circle. Now we also need to look at another type of domain, which is called Circularlyspeed domain. Okay, and here is the definition of it. Again, we take the standard unit circle, and then we move some circular arc. So all these circular arc has a center at the origin. Okay, so the resulting domain will be called Circularlyspeed domain. And there's a classical result saying that there exists a conformal map from the circular domain to this kind of Circularlyspeed domain and up to a unit up to a rotation. Now here is the characterization for proper map from a circular domain to the standard unit disk. Okay, so first of all, let's take P1 up to Pn points in this omega, and let us assume this point satisfying the harmonic measure condition I just mentioned. Okay, and then we also have n1 up to ng. They are positive integer. Okay, and the condition or the characterization for proper homomorphic map from omega to d will be given by this formula here. Okay, so any such proper map can be expressed as a factor here, so exponential factor here, together with a finite product of some map here that I'm going to define. Okay, now this Ni would be the boundary degree of F. Okay, so first of all, let me explain this Vjz here. Okay, so they are called integral of first kind to be defined later, and then eta set P from now on would be denoted as the conformal map from omega onto a Circularlyspeed domain. Okay, so which send P to P. Okay, sorry, which send P to 0. Okay, so fix P, and then this map, this notation here would be a conformal map from omega to a Circularlyspeed domain, and it will map P to 0. Okay, and in addition, it will also map the unit circle, standard unit circle, to the unit circle. Okay, so later on we will see that you can actually write down this conformal map in terms of something called Shocky kind prime function that will be introduced later on. Okay? So we have this conformal map here, okay, and is involved in this finite product here with a different pk here, okay, and because of this condition here, so you can see those pk are precisely the zeros of f. Okay. Now here is just one example. So for this eta function, so this is a circular domain, and we map it conformally to a circularly split domain. Okay, and we map this p to 0, and the unit circle to the unit circle. Okay, and later on we will also look at similar map, but map some inner circle to the unit circle. So that's one example. So eta j from now on would be a conformal map from omega to a circular split domain, such that gamma j will be mapped into the standard unit disk. Sorry, the unit circle, such that it map p to 0. Okay, so here is one example of eta 1. Okay, so this gamma 1 here would be mapped onto this unit circle here. Okay, and p will goes to 0. Okay. And somehow this kind of a conformal map is related to this one by the following formula. Okay, so that's a nice way to transform one to the other one. But the formula involves this function vj to be defined later on. So this is a first integral. Okay, and also a constant. But this constant doesn't depend on z, only depends on the point p. Okay, now using this formula here, we can rewrite our result here. So we want to get rid of this exponential factor, basically. Okay, so and then it's not difficult by using this nice formula to get the following expression for proper map. Okay, so so here is the result. Okay, so p would be eventually would be the 0 set, and we have n zeros, but we are going to group them according to the boundary circle. Okay, so so each of them will sort of associated with a boundary circle. So PLK would be the 0, and L would be from 0 to G, and K would be from 0 to NL. So if you remember, this NL is really the boundary degree of F, restricted to gamma L. Okay, and assume all these points satisfy the harmonic measure condition. Then there exists a proper map with these zeros and sending 1 to 1, and it can be expressed this way. So now I'm using eta L here. Previously, in this case, I use only one map. Okay, but because I want to get rid of this exponential factor, so I'm using other conformal map which send the inner circle to the unit circle. Okay, so then we get this expression here. Okay, again, there's a constant which only depends on the 0 set and doesn't depend on z. Okay, so that's the expression, and we are going to use this one instead of the previous one later on. Okay, now just from this kind of expression, you get a sense that this kind of a conformal map play a similar role as Blaschke factor in finite Blaschke product. Okay. And for application, sometimes it would be good to actually further express this kind of conformal map in terms of something more explicit. And the one that the kind of function that we are going to use is called Shocky kind prime function on this omega. Okay, so it will be denoted by this notation here. Okay, so omega z c. And this eta function can be expressed in this expression. Okay. So I'm going to explain to you the construction of this omega. Okay, so this Shocky kind prime function, which is related to the Shocky group that I'm going to define. Okay, so again, we call that omega is a circular domain with this boundary circle. And for each boundary circle, we are going to define the reflection across this boundary circle. And it will be given by this expression here. So QL would be the center of this boundary circle, and RL would be the radius of it. And it can be, this kind of reflection can be written down explicitly by this formula here. Okay. And then we are going to introduce another map, theta J, which by definition is you first do a reflection across the unit circle, and then you do another reflection across gamma J. Okay, so you will get this map here, and precisely you get this expression, which is just a kind of Morbius transformation. Okay, so you get this theta J G of them, and then you make use of them to generate a Shocky group. Okay, so you generate this a group freely by this generator. Okay, now another notation that I need to talk about is something called Shocky double. So you take this circular domain, okay, and then you look at the image under the reflection across the unit circle. So you get another set here, and then so you put them together with the boundary unit circle. So this omega star would be called Shocky double. Okay, and then you take the closure and quotient by the group that we just generate. So you will get a compact Riemann surface of a genus G. Okay. And then on this compact Riemann surface, already you have some curve, those gamma J, but we also can get some other curve. So here you take a point in this gamma J, and then you take a curve joining this point to theta J inverse Z. Okay. So then you have two family of curve. So this kind of curve will be denoted by sigma J. Okay. So one is the original gamma I, the other one is sigma I. Okay. And then from some result in theory of a Riemann surface, you can find holomorphic function Vi such that these two conditions are satisfied. Okay, so so here this is just the usual delta Ij, and so when you integrate this d Vj over this sigma I, so you get some numbers. So this number are eventually will be a purely imaginary constant. Okay, and all this holomorphic map will be called integral of first kind for the domain omega. Okay. Now this number, they also has some nice properties. I just state here, and in our work we actually need to make use of them. Okay, so these are two useful properties for these numbers here. Okay. And then for the first integral, we also have this equation. Okay. Now, so equation 6 tells you the relationship between the first integral and the harmonic measure in Wang and Yin's condition. Okay. So they are related by this matrix here. Okay. So all these are useful for our proof. Okay. Now, finally, I'm going to eventually give the definition of a Shocky kind prime function. So, so if you fix one of the variable, then will be analytic everywhere in domain omega. Okay, and the zero set of it, if you fix a y, and then you look at the orbit under this Shocky group, then they will be the zero set of omega. Okay, and then you also have this asymptotic condition, and finally there's a transformation law for this Shocky kind prime function. Okay, so these are 4 conditions need to be satisfied, and so it was proven by Shocky that such function do exist. Okay. Now, for application, it would be sometimes useful to have these things more explicit, other than just having some abstract function which satisfy this 4 condition. So, and in fact, under some condition, you can actually express this omega as some kind of infinite product here. Now, this theta prime here is the maximal subset of the group. Take away the identity with this condition satisfied. So if you have one element inside this set, then the inverse of it will be outside the set. Okay, so and it's known that if the Poincare series of the Shocky group converge absolutely, then we do have this infinite product expression for the prime function. Okay, and one case that we are going to use, which satisfy this condition on the Poincare series, would be when all the centers of the inner circles are on the real axis. Okay, so that's a condition that we are going to use, and with this condition satisfied, then we have this infinite product. Okay, and also there are other situations that you still have this infinite product. For example, if all the radius are much smaller than the difference between the distance of the centers, then you also have this infinite product expression. So once we have this infinite product expression, then we can rewrite our conformal map here, this actor here. So we call that this conformal map the outer unit circle to the unit circle. And then, so the circular domain will be mapped into this circularly slit domain, okay? And then we will have this infinite product expression. And M here is a Brodsky factor here. Okay. Okay. Now, using this expression, so we are going to prove a lemma that is quite crucial for our work later on. So let us look at the kind of domain that we are eventually going to consider, which is the following. Okay, so so this is a circular domain, but then we have a family of a circle, small circle, with a same center and radius r, and eventually we will let this r tends to 0. Okay, and we look at this kind of a domain, call it omega r, and in fact there can be a more circle here, but for our purpose, this one would be enough. Okay, now you can map this circular domain into this circular slit domain, and here this is our gamma 1. It will be mapped into the unit circle here, and the notation here is eta r1 p. Okay, so p would be a point here, which is going to send into the origin. And then we are going to look at another domain, which is called omega star. This is the same as the one here, except we don't have this boundary circle anymore. So we just have this domain. Okay. So and then you take a conformal map which map this circular domain into this circular slit domain. Okay. And the conformal map will be denoted by eta omega star here. Okay. Now the question is, if you let out goes to 0, whether this conformal map will converge to this one in certain region. Okay, and this is actually the case. Okay, so for each j, we have this kind of conformal map eventually converge to this one in a smaller product region. Okay, so here R prime is something greater than R. Okay. So that's this result turns out to be quite useful. Okay. Now we are ready to explain how to get this result. So I'm going to mainly focus on how to get a disconnected ball, okay, for certain omega. So instead of looking at the Carathéodory metric, so I'm going to just look at C omega star, okay, and consider the ball given by this C omega star, okay. So we call that the omega that we are going to consider has a connectivity G plus 1, okay, and this G has to be greater than or equal to 1, okay. And so we are using this notation PG plus 1 omega to denote the family of degree G plus 1 proper map from omega onto D, okay. And so from the result of Gransky that I mentioned before, so the Supima in the definition of this Mobius distance would be attained by some degree G plus 1 proper map inside this space. Okay, and therefore this distance can be written this way. Okay, so again we have this kind of a Supima, but this time you only need to consider proper map of degree G plus 1 instead of any holomorphic map. Okay, and furthermore, we can also restrict ourselves to those map which send 1 to 1 according to the uniqueness property of this kind of proper map. Okay, and then we need to make use of theorem 4, a special case of it. So for us, we are only interested in degree G plus 1 proper map, and therefore that kind of proper map has a simpler expression which is given by this finite product here. Okay, so here you have a G plus 1 factor here, and eta j, they are just the conformal map from circular domain to Circularlyspeed domain. Okay. And of course, we assume those Pj, they satisfy the harmonic measure condition. Okay. So we are going to make use of this expression very soon. Okay. Now, take any point inside omega, okay, and then we look at this set. Okay, so this is a set consists of some subset in omega. Actually, each subset consists of G points, so that this point pair up with the given P tilde will satisfy this harmonic measure condition. Okay, so for each P tilde, we just look at the solution for this system of equation. Okay, and now here is one useful observation. So if you let this P tilde tends to gamma 1, one of the interior circle, then we know that from the harmonic measure U1, so the value here U1 P tilde will tend to 1. Okay, and therefore all the other, and also all the other Uj P tilde 0 will goes to 0 just by the definition of the harmonic measure. Okay, and then you make use of this condition. So notice that all this number has to be greater than or equal to 0. Okay, and if you have one of them getting close to 1, then the others will basically tend to 0. Okay, so that's why you get this condition satisfied. So for each pk from 1 to g, the value evaluated at U1 will goes to 0. Okay, and therefore, just from here and using the fact that those are UI, they are harmonic measure on the boundary. So this PK actually will tends to other boundary circle of omega. So that's something useful to know. Okay. So again, we have this space here. Okay, so that if we take a p tutor in omega, okay, and also take a p, a subset in this space here, okay, so that this condition satisfy, and then according to the result, we know that there's a unique degree G+1 proper map from omega to D. Actually, we can write it down, okay, which map 1 to 1, and we are going to denote this proper map by this notation here. So phi omega p tutor p. Okay, so eventually this p together with p tutor will be the zero set, and this one will be just the proper map. Okay, and then Möbius distance. We call that can be written this way. So this is the space of degree G+1 proper map. Okay, and then you may identify this kind of proper map with this kind of a point capital P here. Okay, so and using this notation, okay, so this supimum here is attained by some proper map here. Okay, so this C star omega is actually the same as taking the supimum of all these proper map, where P is any one in this set here. Simply means P1 up to PG together with P tutor, they satisfy the harmonic measure condition. Okay, so you look at all. In some sense, we actually parameterize the proper map of a degree G+1 with 1 0, which is P tutor. Okay, and then we go back to this ball here. Okay, so this is open ball, and this is just the definition of it. Okay, and then this distance can be expressed in terms of the supimum I just mentioned. Okay, so this distance is really the supimum of all this kind of proper map, where P is just a set inside this space. Okay, and then if we define using this notation, we define a BP to be this set. Okay, it's just coming from here. Okay, then this set here is really the intersection of all these things. Okay, so over points inside this parameter space. Okay, so in other words, we can write down this open set, open ball, in terms of the intersection of this kind of set. Okay, and then the next thing we are going to do is try to look into this kind of subset. Okay, okay, now we go back to this proper map. Okay, and according to our result, you can just express it as some finite product of conformal map. Okay, so it's given here. So there's a constant which is independent of a set. Okay, and so all these mappings, they are just the conformal map from circular domain to the circular slit domain. Okay, and of course, we know that, for example, this one, if you replace that by P tutor, it will be equal to 0. Okay, and here, if you replace a set by Pj, it will also equal to 0. Okay, so so this is the conformal map which map the unit circle to the unit circle, and this one is the conformal map which map gamma j to the unit circle. Okay. Okay. Now let's go back to the kind of domain that we are going to investigate, which is this omega r. And this is a small circle with a, so this is actually a gamma r is a family of a circle with the same center and radius r. Eventually, we will let this r tends to 0, okay? And so the idea is the following. So if we take a p tilde and let it approach to, say, gamma 1, okay? So according to the previous discussion, all the other zeros will tend to other boundary circle, okay? So that's the first step. So in other words, there will be a circle, a zero very close to this gamma r, okay? And then we make use of lemma 6, which says that this kind of conformal map eventually will approach the conformal map, which map the region without this circle. Okay. And using this fact, okay, so it's possible to find some little r so that we can also find some theta, which is close to this circle. Okay. And this circle, so this theta is chosen to be sort of far away from a neighborhood of p tilde. Okay. And using this lemma, we can prove that if you look at the finite product here, okay, so one of the term here will be arbitrarily small, okay, at this point theta, and all the other terms are bounded. So here we really need to have we eventually need to have to use the fact that G is greater than or equal to 2. Okay, so in other words, we have 3 boundary circle here. Okay, so so the conclusion is because one of these terms is arbitrarily small, the others are bounded, then the whole thing is arbitrarily small evaluated at this point theta. Okay, so this is small, okay, and on the other hand, if you replace this theta by p tilde, it has to be equal to 0 just by construction. Okay, and therefore, if you look at this set, okay, so this is the kind of the set that we consider. These 2 points would be inside this set, okay, for each p. And finally, we need to prove that these 2 points cannot be connected by any path within this set. Okay, so this is the technical part for the proof, and then we call that our ball can be written as the intersection of all this kind of set. Okay, and from here you can conclude that the ball is disconnected. Okay, so that's the basically the sketch of the proof. Okay, so I think I shall finish here. Okay, thank you for your attention.
Patrick, thank you very much. Let's thank Patrick. And questions, comments, suggestions? Well, if there are no questions, let's thank Patrick again for wonderful talk.